Okay, these are the notes you should have found. If you weren't here last time, you need to go watch the video. It's on Canvas to get the first part. Remember how we watched Men in Black clips? What was the part of that? Evan? The world big and scenes. You guys knew everything about numbers, right? There's a whole world beyond the real. It's called what? Imaginary. And at the very end, so we went through all the different number systems that you've already learned, and then we added a new one, imaginary numbers. The two things you have to memorize from imaginary numbers. The square root of -1 is I, right? That's what we see in imaginary numbers. We can't take the square root of a negative. And I squared is actually a real number, -1. And then we'll learn what a complex number was. Oops, this must be the other classes that didn't make it all the way through examples. Then we learned what a complex number was, right? A complex number was a real number plus an imaginary number. Okay, so we have two pieces. There's one form A plus BI. So A, in this case, is 5, and the imaginary part is 7i, which we can still graph. Normally, when we graph our normal style graphing we're all used to called the rectangular coordinate system, we can graph 5, 7 by going right 5 up 7, right? Okay, I'm going to, there's something here that I don't want you to see yet, so I'm going to put the coding up really quick. Okay, hold on. Get that down. Okay. Okay. Graphing with a complex number 5 plus 7 is pretty much the same, right? The x-axis, the x-axis is actually going to be the real axis, but the movement's the same. The first number is your left and right movement. The second term is your up and down movement. But the vertical axis is no longer the y-axis. What's it called? The imaginary axis. So it's labeled 1i, 2i, etc. up to 7i. So we still have right 5, up 7. Okay? So I want you to try graphing. How to figure that. I'm just going to show you the answer. I'm going to make it really quick. Yep, I'm going to show you the answer. Just delete all that stuff. Okay, much better. Okay, we're going to call it example 1. I know we already did one in graphing 1, but we're going to practice graphing a couple of complex numbers, and we're going to use those same problems to calculate one other thing. So I would like you to graph the complex number 5 minus I. So we need to draw a new graph and label. What's this vertical axis called again? Imaginary. What's the horizontal axis called again? Real. If you don't label these, then the person reading the graph would probably assume it's the rectangular coordinate system. That's not the case. This is the complex coordinate system. Okay, so we need a label. We should also label our tick marks. 1, 2, 3, 4, 5. 1, 2, 3, 4, -5. On my imaginary axis, what am I counting by? What's my first tick mark going to be? It's not 1. It's I, 1i. Then we get 2i, 3i, 4i, etc. Then that would be -i, -2i, -3i, etc. Okay? So after you have it set up, graph the complex number 5 minus I. Then I want you to compare with your neighbor so you get the same thing. And the third chamber should share USB receiver and so you should put it in the same spot. Okay, Will, how do I move from the origin to plot 5 minus I?
Well, I don't know if this is correct. Because
No, so the first number is your left and right movement, and then second number is up and down movement. Okay, so if the first number is 5, and it's left and right, which direction will we go? How many? 5, good. And the next one is negative I, and where is negative I? Up and down. So since it's negative, we're going to go down to there, right? So it makes sense? So first number, left and right. Second number, up and down. And if it's positive, you go up, if it's negative, you go down. Okay, so that is the number 5 minus I. Okay, let's try another one. Example 2. Graph an extreme as 2I on a new coordinate complex plane. So you relabel, real, imaginary, normal is label, that is counting by. And imaginary will have eyes on it. And then compare with the neighbor if you see you put it in the same spot. If you did it, you discuss why you put it where you put it if you feel confident. No pressures. Okay, kids are coming out the crafters. I want you to compare it with their own. You give a thumbs up if you agree, thumbs down if you disagree. Thumbs up or thumbs down. Agree or disagree. Good, I agree. Good. So the first number is left and right movement, switch to the left. Sorry, I'm trying to find what it is. And then the second number is up and down, since it's negative, she went down. Down? Okay. Now we're going to find the absolute value of both of these numbers. Who knows what the definition of absolute value is? Jake? Excellent. Because the absolute value of 5 is what? 5. If the absolute value is negative 5. 5. Why is both of those positive? Because that doesn't make sense to measure distance in a negative length. Lengths and distances are positive, right? So that's why they're both positive 5. So if we are on a two-dimensional graph like these, our distance from 0 would be distance from the origin, right? Because the origin would be 0, 0. So we're going to find the absolute value of each of these points. It comes from the Pythagorean theorem. Okay, so let's see. Yeah. Absolute value is, just a reminder, so value is distance from 0. Okay. So this point right here, 5 minus I, is distance from 0 is that length, right? That makes sense? So that could look at kind of like slope right from that point, I rise, and then I run. What does that create with my blue diagonal? A right triangle. And the blue part of that right triangle is the part of the triangle. What? The hypotenuse, yeah? So it comes from, the part that we're going to be using comes from the Pythagorean theorem. Hannah, do you remember the Pythagorean theorem? No? Oh, shoot. I'm going to go with the Pythagorean theorem. Yes, there you go, Hannah. Okay. Hannah, do you remember now which letter is the hypotenuse? Oh, summer amnesia. Let's have that from here. This is me. You tell me which B? C. Which letter represents the hypotenuse? A, B, or C? Yeah, it's always C. C is the hypotenuse. So if we were to solve for C, then help us give it the hypotenuse. What's the inverse of squaring? So we can get rid of that square. Square root. So essentially we have the square root of A squared plus B squared. That equals the hypotenuse. This formula, when I solve for C, is actually called the distance formula. And that's essentially what we want. We want distance from 0, right? So the absolute value of a complex number, A plus BI, equals the square root of A squared plus B squared. Because that's a made-up formula. There's actually a relation. It comes from the Pythagorean theorem. So the distance from the origin is the square root of A squared plus B squared. Okay? So our next example, example 3, using that same problem above, we're going to find the absolute value of the following. That was 5 minus I. So absolute value, make sure absolute value bars are big enough and they don't look like ones. Absolute value of 5 minus I is the square root of A squared plus B squared. Okay, A is our little piece, B is the coefficient of the imaginary term. So on this problem, theoretically, what is A? Usually, what is A? Good, it's 5, yeah? So we're going to square it, 5 squared. What is B? Here's the error. Okay, so one person has it, 2 people have it. P is the coefficient of I. It's not the I. What's in front of the I? -1. So B squared will add, in parentheses, -1 squared. Okay? If we simplify that, oops. We get square root of 25, that's 5 squared, plus -1 squared is 1, which gives square root of 26. Doesn't follow that? Okay, before you say that this is your answer, you have to see if it breaks down, because it should be in simplest form. Okay? Rachel, what are 2 numbers that multiply to 26 to help us break down the square root? Oh yeah, you can do this without a calculator. It's even, right? 26 is even? Okay, good numbers. 2 times 12 would be 26, so that's half of 26. There you go. 13. So we have 2 and 13. 2 is prime, because we circle that all the time when we do factor trees. What about 13? It's also prime. So are these pairs? No. So can you put all of the square root? No, but you need to make sure you check. Some of your homework has stuff that proves out, so remember to look for pairs. So the absolute value of 5 minus I equals root 26. That's the distance from 0. If the directions don't say round a decimal, then you should not be putting that in your calculator and writing a decimal. This is called the exact form. When the exact form that you give in the square root. Okay? Let's try the other one. Same thing, find the absolute value. But what's the other problem? Negative 3 minus 2i. The same one we graphed above. Okay, I want you to work it out for yourself. Number is the square root of a squared plus b squared. But you don't ever insert an I. B is the coefficient of the imaginary term. And always use parentheses, especially around the negatives that you insert. Because there's a difference of negative 2 without parentheses squared versus negative 3 in parentheses squared. Those are different values. Okay? And check your answer with the breaks down. Okay, Clayton, what do you get? Square root of what plus what? Good. So, how many do your simplification get square root of? Okay, 9 plus 4, which is square root of 13. Does 13 break down? Why? It's prime. So, that's the value is our distance from 0 and square root of 13. Any questions there? Yeah. That's the most proper way to write it. And the whole thing. Remember equations technically, we should carry down the whole equation. Okay. Now we're going to move on to adding, subtracting, multiplying, and you guys get to do dividing, which is a lot of fun. But you already know how to add and subtract these, so it's not going to be anything new. Add, not adding, add and subtract complex numbers. If you didn't even know about imaginary numbers and complex numbers, you still would have been able to do these correctly. Example 5. 7 minus 2i plus negative 3 plus I. These are two different complex numbers. The first one in parentheses is a complex number because there's a real piece and an imaginary piece, right? You see the real part and the imaginary part? The second one is a complex number. Does it have a real part and an imaginary part? Yeah, negative 3 is real, I is the imaginary. If you didn't even know about imaginary numbers, how would you go about adding these two together? Yeah? Like terms, exactly. So nothing different. I like terms. The real piece plus the real piece. Those are like terms, right? 7 plus a negative 3 is just 4. What other parts are like terms? The imaginary pieces. Imaginary plus imaginary. Negative 2 ice creams plus 1 ice cream. What's that? Negative 1 ice cream. So you can put the 1, but we don't usually do that. Next is standard form. So standard form looks a little different than we're used to because the variable I is last. Because we have the little piece first and then your imaginary piece second. Okay, let's do this one. 1 plus 5i minus 3 minus 2i. When you try that with any word, and be careful, because you know, our first test, if it was our first test, had problems like these, right? Just combining like terms. That subtraction has one extra step, so don't forget that subtraction has one little trick that you have to do first. So what's the first thing we have to be careful about on subtraction? A negative what? A negative 1. That's hiding in between the two coefficients or the two complex numbers. What do we have to do with the negative 1? Distribute it in. So we have negative 3 plus 2i. So you have to make sure you change the signs. So the real piece is 1 minus 3, we should have negative 2. The 5 ice creams plus 2 ice creams is plus 7 ice creams. Okay? Any questions about adding and subtracting? Yeah? And before I go on, we can write like that. Well, there's 2, that's why I generally do the parentheses. Okay, so essentially the steps. Distribute if necessary, that happens with subtraction. Then we add the real parts, add the imaginary parts, and then make sure it's in the right form. Make sure our answer is in the form A plus BI. It's pretty similar to just adding polynomials. Okay, multiplying polynomials is also very similar to what we're used to, except for one new detail. I gave this a multiplying polynomials, but multiplying complex. Example 7. 7i times 3i. Remember how complex numbers are supposed to have a real piece plus an imaginary piece? What's the real piece of 7i? 0. So this is still technically a complex number. 0 plus 7i. That's the same thing as 7i. Is 3i a complex number? What's its real piece, John? 0. Yeah, 0 plus 3i. That's 3i. Okay? So normally, we do 7i times 3i, and it'll give you what? 21 squared, I squared. However, when I told you to memorize 2 things. Oops, I made that. 2 things. The square root of negative 1 is what? I, and I squared is negative 1. I squared is a real number. So we have to convert this I squared. You can never leave I squared in your answer. You can't even leave I to the even power, because I to the 6th has how many groupings of I squareds? I to the 6th has how many groupings of I squareds? 3, 2 times 3 is 6. So each being to the even power can be converted into groupings of I squareds. So you make sure that you change all of the I squareds back to a real number. So we get 21 times negative 1 is negative 21. That's really interesting. An imaginary times an imaginary, does it give you an imaginary answer? No, it gives you a real answer. An imaginary times imaginary crosses over back into the real world. Negative 21. Okay, a little harder one. Example 8. 2 minus 3i times 4 plus 5i. How would you normally just put 2 binomials together? Just trade, okay? You guys all can do that. So So distribute, this requires double distribution. And then the trick at the end was to remember to take your I squared and change them to negative ones. Stand up when you think you have the answer. And all of your I squareds have been changed to negative ones, and it's in proper form A plus BI. One more step. One more step. I think it's a 22. Look at your eyes again. Yes. 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 Yep. Yeah, that's good. Remember that's down, combine your right first. Good. Which was that? No, over there. So it's just not in the right form. What order should it be in? Standard in this case, that means real piece plus the imaginary piece. So you got your I. 10, is that a minus? Yeah, it should be negative 2I, we forgot that part. Okay. Let's see what we have. Okay, one more step. We're going to get it right turn through. So put a relation with 15, aren't you? 15. Remember that 15, that's the way we're 15. Minus 7 is not right. Because this should be a 15. It should be a positive, which is also a negative 1. 8 plus 15. Then 8 minus 15. It's 8 plus 15. Okay, how long here? Let's go. Solve it on the board. Okay, step by step. If I told you you have one more step, I think most of you mentioned figure that out. You have to combine like terms 2 different times. So, if that's what it does, you do agree. Okay, so I'm going to slide really quick. You guys did that step? Yes, I agree with that too. Okay, keep going. Can you explain to us what you're doing on this step? Okay, terms, the i's. 10i minus 12i is negative 2i. And what are you doing right here? Change what? I squared has to be changed to negative 1. You did 2 steps in one line, which is totally fine. You can do it in one line if you use that. Okay? Then, a negative 15 times a negative 1, is that actually a positive 15? Yeah. So we can stop here, but why do we not stop here? We have 2 real terms now, because the I squared makes that term a real number, so we have like terms again. So what's our final answer? Okay, great. And he box it up. Thank you. Now, some of you got, you did 8 minus 15, I got like a negative 7. So then it should be positive because it was a negative 15 times a negative 1. Any questions on that problem? Okay, before we transition to division, let's all stand up. Stand up. We're going to take a break really quick. Stand up. Everyone up. Let's move around a little bit. I want you to go fine. Okay, we're going to quickly cover a couple of simple topics that you need to know for homework before we hit the division. Okay, first of all, homework notes, so just call it. Now, just keep going with the notes. What is the square root of negative 9 times the square root of negative 49? Would we do plus or minus 3 times plus or minus, plus or minus 3i times plus or minus 7i? Or can we do it different way? How do you multiply out of this? Yeah, just like fractions. Do fractions have to have a common denominator to multiply? No. Common denominators we add and subtract. So just like fractions, multiplying is multiply straight through. So I'm going to switch here into negative 9 times negative 49. So we're going to calculate what is negative 9 times negative 49. So if 141, someone else with a calculator. Can you keep the square root of that and then you already get 21. Now this one, I'm not going to put plus or minus 21 because the true rule of thumb is if the square root is already printed in the problem, it's already told you the sign of the problem. Is there a negative sign in front of the square root? No. Is there a negative sign in front of the square root? No. So it's in the positive and the positive, which is a positive. If you apply in the process of solving an equation, sometimes we apply the square root ourselves to under a square. If you apply the square root yourself, that's when you get a plus or minus, because you don't know if it's the positive version or the negative version. Okay, so this would just be positive 21. What about square root of negative 1 times square root of negative 16? That becomes the square root of what number? Positive 16, which is just 4, right? So just a quick refresh on how you multiply radicals together. Okay, some vocabulary that you probably learned in 7th and 8th grade math that also applies to complex numbers, and things like the additive identity. Okay, what is the additive identity of 3? This is the number we have to add, and we get its identity back. To get its identity back, does the number change? No. So what number might add to 3 to still get 3? 0. That's for regular real numbers, right? An additive identity has something you add to get the identity back. The identity doesn't change, it's the same identity. What about the complex numbers? What if I gave you 5 plus 4i? What do we have to add to get our complex 5 plus 4i back? Just enough? It would be 0 plus 0i. Because the real piece is 5 plus 0 is still 5, right? And 4 plus 0, 4i plus 0i is still 4i. So additive identity gives you the identity or the original back. Additive inverse is different. Because inverse is when we're solving. What's the inverse of addition? Subtraction. Why? Why are those inverses? completely undoes it, right? So we're going to do it as opposite. So it will be 5 plus what would equal 0, essentially has to be eliminated. 5 plus what would be 0 with its additive inverse. -5, because they were completely eliminated, right? So that's what we're going to do for the complex numbers. If I have -3 minus 2i plus the minus additive inverse, which means that the inverses they should cancel each other out. So I'm going to say no, the complex additive inverse. Okay, the same answer. Waiting for just a sec. Hannah? 3 plus 2, I think we'll get that. Do you agree? Disagree. Thumbs up, thumbs down. You agree? Disagree. I agree. So -2 plus 3 is 0. -2i plus 2i is also 0. Okay? I'm going to clear additive inverse versus additive identity. Identity with the original back inverse has to eliminate. Okay? And the next one is called a conjugate. I don't know if you've heard about before. Has anyone heard of a conjugate? Conjugate is, maybe the complex conjugate. And this is what we need for division in order to solve these division problems. Okay? The complex conjugate is pretty much the same complex number, just the operation in between changes. So sometimes you see it written as V bar. Okay? If our complex number was A plus BI, the conjugate, so the bar, A plus BI, the conjugate of A plus BI would just be A minus BI. So it's the same complex number, but the operation in the middle changes. That's the only difference. They don't both change signs, just the operation in the middle changes signs. And we need that in order to answer division problems. What is the example on? 9? Thank you. Dividing complex numbers. Example 9. Okay, 2 over 3 minus I. They're really picky, mathematicians are, on how they like the answers to look like. We like answers in standard form, right? We like the number. If we have a variable and a number, we don't write like that, right? How do we write a variable times a number? The number first, and then the variable. It looks pretty odd. We like it all organized in a certain way. We also never ever do these things. Never we just talked about 1 in our answer. I experienced, right? Never leave that in your answer. Also in fractions are really picky. Never leave in the denominator. Never leave, speaking of negatives, with, that's not doing never leave, is negative exponents, right? Negative exponents. We don't like those in our answer. We leave, oops, I meant to say in the denominator. There are a lot of things we don't like in the denominators of fractions. We never leave fractions in the denominator of fractions. We never leave square roots in the denominator of fractions. And we never leave i's in the denominator of fractions. So let's have a problem. We have an I in the denominator of the fraction. So we have to force the I up to the numerator. It's the same, very similar process to forcing the square root up to the numerator. Just called rationalizing the denominator. You know that before? No? What if we had 4 over square root of 2? How do we force the square root up? You times by an empty form of 1. Root 2 over root 2. Because the numerator will now have the square root of root 2 times root 2, which is root 4, which is 2. So the square root gets forced up now using my square root 2 root 2. And the square root gets forced up by using this fancy form of 1. But the same thing here, the fancy form of 1 has to be picked strategically. But you just have one term in the denominator, we have a real term and an imaginary term. So we need all of the i's to disappear. So our fancy form of 1 is going to be the conjugate. Most of the time we use the conjugate from the denominator. As you get into more advanced math, such as calculus, we found this a handful of times, that sometimes the conjugate of the numerator is very helpful. So this is our complex number 3 minus I. What's the conjugate of 3 minus I? 3 plus I. So if I multiply 3 plus I in the denominator, do I have to also do it in the numerator? Just a fancy form of 1. I would probably put parentheses around that too. Okay? So, we just multiply the 2 property, 2 times 3 is 6. 2 times I is plus 2I. Would we have an I in the numerator? Yeah, no problem. Okay, if not, we will use the complex conjugate, and because something nice is going to happen. 3 times 3 is 9. That is 3 times I. What is this? What's 3 times I? 3I. What else do I need to multiply? Negative I times 3, which is negative 3I. And lastly, negative I times I. And negative times positive. Negative I squared. Look what happens. What happens if these two in the middle? Cancel out, and as long as you use the correct conjugate, which is the same thing as choosing sign in the middle, you're going to cancel in the middle. Which is perfect, because all of my i's disappear. I'm left with a 9 minus, in the I squared, actually a real number. What is I squared? Negative 1 like this. What did I do wrong? I do minus a negative 1. So be careful there. It's minus I, it's minus a negative 1. And all the i's are gone. So I get 6 plus 2I over 9 plus 1 is 10. Now I would almost say that was my answer. Almost. But between the 6 and the 2 and the 10, I can see something that I need to do to simplify. Great common factor, exactly. Great common factor, Captain. 6, 2, and 10. 2, because they're all even, right? So I'm going to divide the 6 by 2, which gives me 3. I'm going to break it apart too, the real piece and the imaginary piece. This is one big fraction, and the 10 divided by 2 is 5. So there's my real piece, 3/5. Plus 2I divided by 2 is, it's just I. Is it just I, or is it going to be a fraction? I over, no, 10 divided by 2 is 5. We already both have and I put the I on the outside like that. Then we both have the denominator 5. So 3/5 plus 1/5 I. Conjugate is the same, like binomial, but in this case it's a complex number. It's exactly the same, except for they have different signs. If this is minus, then the conjugate is plus. Okay. Some of these can be a little intense. So, I'm going to pick one of the more difficult ones. We're going to run through really quick. This will be our last division one. Okay, I'm going to borrow difficulty so you at least see the more difficult one. It's very important to know that this I is not underneath the square root. Okay, the square root ends where the I is written. Same thing here, the I is outside of the square root. So write an expression in standard form without using a calculator. Well, yeah, I would use a calculator anyway. So standard form is like this one, where we have the real piece separated from the imaginary piece. Okay, the problem here is that two problems actually. There are two things in this denominator we can't have. I and the square root. There's two problems, so we need to fix that. And the easiest way to push those up is by using the conjugate. Can you trick your neighbor to tell your neighbor what the conjugate is? Okay, Charlie, what's the conjugate? Root 2 times A. And what do we do with it?
You multiply the top and the bottom.
Good. So this is our fancy form of 1, right? 1 minus square root 2, and the I is not underneath the square root, it's outside. Divided by 1 minus square root 2I. Alright, the numerator has a lot of work to do. How would we normally multiply a binomial times a binomial times a binomial? What? No, that's factoring the trinomial. We did one of those on our last test, and a test review problem. We had 3 binomials. Is money? Right, just focus on 2 at a time. And then when you take that answer, then you multiply it to the last one. So, I'm going to look at the first 2 first. Okay? Would you multiply those together very carefully, and then stop after you combine the right terms? This can get very tedious, so don't go too fast that you make a mistake. And we'll be one sign error, and the whole answer is going to be wrong. Just do the first 2 complex numbers multiplied together and then stop. So make sure that I don't make a mistake. And then find the right terms. Okay, let's do the last one. What is negative 2I times I? Negative 2I squared. Right? And these 2 in the middle, what terms? Technically, yes. But what is 1 minus root 2? Is that something we can write easily? No, so this one I'll leave it as is right now. What can change with the I squared? What is I squared? Negative 1. So this is negative 2, negative root 2 times negative 1. Wouldn't I just get positive root 2? So plus root 2. So I'm going to take that I'm going to times it by my other complex number. This is all over 1 plus root 2I times 1 minus root 2I. Okay? Just take a step at a time. We're still working on the numerator. The denominator will be the nice one because of the conjugate, things will cancel out. The numerator is a little intense. So now we have 4 terms, which is a polynomial. This is a complex polynomial, times 2 terms. So be very, very careful. What is 1 times 1? And 1 times negative root 2I. I'm sure we'll think about that. But negative root 2I. Just do a piece at a time. Okay, Toby, what about this I? When you type in the I, what do we get? Negative root 2 I squared, which we're going to have to fix I squared in a minute. Okay? Oops, I don't want that color. Let's try this color. Now we have to take the negative root 2I and times it in. Negative root 2I. Bryson, what's the negative root 2I times both of those? Ooh, you got a hard one. What is it? Root 2 times root 2. Root 2 squared, which is root 4, right? What's the square root of 4? 2. So root 2 times root 2 is going to be 2, and I times I is I squared. Okay? And then lastly, root 2 times 1 and root 2 times that. Make sure we leave it there. Root 2 times 1. So positive root 2, right out in here. And what's root 2 times negative root 2I? That's root 2 times root 2. Root 4, which is, square root of 4 is 2, and this is a positive times a negative. What's a positive term times a negative term? So we have negative 2, and does this one have an I? Times this one that did have an I, so how many I's are there? 1. Whew. That's intense. To save on space, let's go ahead and do the denominator. And then we'll start finding that cancel out. The denominator, though, is nice. Not as hard and difficult as the numerator. So would you go through and multiply in the denominator? And you should see, because we use the conjugate, the middle term should cancel out. So write it right underneath that big long stretch we did there in blue and green. You should see the middle terms cancel out. If you don't, then you probably need to check your work. That's how the conjugate is designed. Middle terms will cancel out every time. Okay, what did you get in the denominator? Square root 2I. How about the square root of 4? So 2 and then it was I times I actually. I squared. Okay, do the middle terms cancel out? Yeah, negative root 2i, positive root 2i, they cancel out. So the next line, I'm going to fix all my I squareds. In the numerator, I have, actually, let's see if there's anything that cancels out automatically. I don't think I see any that cancels out. 1 minus 2i plus I minus root 2. What happens here? Minus root 2i squared would become what? What is I squared? Negative 1. So this is negative root 2 times negative 1, which is what? Positive root 2. So I'm just going to make that a positive root 2. Minus root 2i. We have another one. 2 times I squared. I squared is what number? Negative 1. So 2 times negative 1 is negative 2 plus root 2 minus 2i. Whew. Really, that's the hard part. The denominator is so much nicer now. 1, and then what happens here? We have negative 2 times I squared. What does that become? Positive 2, because this is a negative 2 times a negative 1, which in total makes positive 2. Now what in the world can we do? Simplify how? Okay, so that's clean. Done. Now what?
And you would combine all of my life.
What are the right terms?
For our real numbers, it's
Okay, so I think that's too far out. We need to find all the real pieces, right? So let's find all the real pieces. This one's real. So if it doesn't have an I, it's real. That one's real. This one's real. And this one's real, right? Some of them are easy to combine with. I'll fill it in. The 1 could easily combine with which other real number? Negative 2. So let's do those. 1 minus 2 would be negative 1. Yes? So then we can find out. This one? Yeah, you're right. Thank you. Hi. Oh, what is it? Oh, I guess I should talk about that. Yeah, just put it in that little slot. Thank you. Is it the first topic of the day? Okay. Okay. Thank you. Alright, so those two we can combine. What about the empty parts? We have root 2 plus root 2. What is that? You have anything? 2 roots of 2. They're like terms, right? Roots of 2 is the last thing. This one has 1. This one has 1. So there's 2 roots of 2. So plus 2 roots of 2. All over what was the denominator? 3. Remember, it's not pretty looking. Now we're going to do the same process with imaginaries. So here's an imaginary. Here's an imaginary. Here's an imaginary. And here's an imaginary. And let's start with the pretty-looking ones. Which ones are pretty-looking out of all of this start? The eye, so maybe I'll color in my star. That's a nice colored in star. And there's another one, right? Negative 2i. So out of the pretty-looking eyes, how many are there? 1 minus 2. What's 1 minus 2? Negative 1. Negative 1. And this will all be an I. The I comes after the fraction mark. It will all be I's. Negative 1. Then what about our roots of 2? This is a negative root of 2 minus a root of 2. So that's like the last name. Then we have negative 1 This one has -1, so how many total are there? -2. Roots of 2, and that is all in the I family, all but 3. That is a plus right there. Another alternate way to write the same answer, since both of those are negative, I'd rather you just give a plus so you keep the signs the same, but I could make the whole fraction negative, which means the 1 is positive and the 2 is positive. I think just put a plus in between them and keeping their signs the way you find them is the easier way. Okay, so that's one of the really intense ones. So we start the real piece and an imaginary piece. It's not so pretty looking, but it's there. In your books, especially if you have your volume 2 books, I want you to find where the honor section is. They look at the volume 2, there's a dark section, the strip is dark. Those are the honor sections. Homework is going to be on page 32. That's the page number. So the back of the book, page 32. So I want you to be able to find where that is. Open it up until you find page 32. It should say complex. So not too far. Yeah, it should say complex numbers. The section is H4, but the page number is H32. So if anyone doesn't have a book, help show them where they're going to find their homework. H32. And actually, you know what, the homework actually doesn't start until H35. So I'm going to actually make your homework is H35. That's where the homework problems actually start. Okay, and we are going to do... Make sure these are all. Okay, let me do it. We're going to do 2 through 40 even. 2 through 40 even. The problem we just completed was number 40. So that's the hardest one in the book. Because the hardest one was the last one, right? So this is number 40. So you need to make up it on your homework. And really you only have 19 more. But it starts off with the easy ones. Adding and subtracting, you can do that. Multiplying, just remember the I-squared has to be changed to -1. Okay? So everyone is already able to find where the honor section is in the book. Please bring this book with you to pass its time. Okay. You have a calculator in mind? Please make up to the front.